Lad- Ladies and gentlemen, a very good morning to you all. My name is Dr. Selima Khatun, an assistant professor of botany in Maulana Azad College, and it's my absolute pleasure to extend a hearty welcome to each one of you present here at the online refresher course on Bioscience, Bioengineering, and Nanotechnology organized by UGC-Malaviya Mission Teacher Training Center, University of Calcutta in Maulana Azad College, Kolkata. We are thrilled to witness such enthusiastic participants and a highly learned audience gathered to deepen their understanding of this significant topic through this refreshers course. We are fortunate to have with us today a distinguished speaker, Dr. Rupak Roy, is a research scientist specializing in energy and environmental biotechnology with expertise in biomass utilization, waste to energy conversion, and nanotechnology. He holds a PhD in chemical engineering from NIT Agartala in 2022, focusing on lignocellulosic biomass conversion for clean energy. His interdisciplinary background includes an MSc in biotechnology from Ravenshaw University and a BSc in biochemistry from University of Calcutta. He has 40 plus research paper, 500 plus citation, 4 book chapters, and field 3 patents. Dr. Roy has made significant contributions to renewable energy and environmental sustainability. His key research areas include biofuel production, nano bioremediation, and green nanotechnology for pollution control. Currently, he is a research scientist at SHRM Biotechnologies Private Limited, working on bioprocess optimization and renewable energy innovations. He is also an industry expert and board of studies member at one of the eminent colleges of West Bengal, shaping academic curricula. Dr. Roy has presented at over 10 international conferences, delivered multiple invited talks, and received prestigious awards, including the Best Industry Academia Collaborator Award in 2024. He serves as an editorial board member and peer reviewer for leading scientific journal. His future research aims to integrate AI-driven nanotechnology for pollution control, develop sustainable biomaterials, and advance zero waste manufacturing, contributing to a cleaner and more energy efficient future. Mm, Dr. Roy's speech is in two halves. After completion of presentation, there will be an interactive session for 10 minutes to clarify your queries and doubts. As we set out on this intellectual journey, we hope that this seminar will offer all attendees a plethora of insights, enable fruitful interaction, and inspire fresh perspective about the topic at hand. Without further ado, let's begin our journey into the intriguing world of bioscience, bioengineering, and nanotechnology. I am honored to invite Dr. Roy, our distinguished speaker of the day, to share his valuable insights. Sir, please start your lecture.
Good morning to one and all. Thank you, madam, for such an elaborate and lovely introduction. Namaskar to all, everyone present over here. As I'm already mentioned my details, so I'm Rupak, and I have been serving at SHRM Biotechnologies for the last 5 years as a research scientist. And prior to that, I did my PhD in NIT Agartala, and my topic was more into model optimization, statistical modeling, data interpretation, and all. So although I did my MSc in biotechnology, but thereafter I shifted my domain into, you know, engineering aspects, and where I learned more about these mathematical approaches, like how we can sustain our research, how we can propel our research without using minimal amount of inputs. So today will be I think it's going to be more of an interactive session, because I will be dealing with some sort of statistical modeling in the form of RSM, or response service methodology. You all must be knowing these things, but still I will be digging more, giving an insights that how you can adopt these schemes into your expertise, into your experiments, your research, and get fruitful results. I up to MSc, I have seen conventional research, which are mostly done in the field of scientific domains. But as I have switched to the engineering domain, I found out how smartly they work without using minimum resources, and it's actually very good to see that how all these things could be adopted at industrial scale, because at the end of the day, industry only demands for two things: time and money. So if whatever the research is, if it is not financially feasible or timely time bound studies, then it's of no use in the industrial scale, because there are always emergencies. We can get some insight from the COVID-19, like how that pandemic hit us, and how we you know we got a vaccine within 9 to 10 months within our year. So these fast tracking things, these propulsions are really very much important. uh, in the first half, I will be giving you a brief demonstration, like how we can adopt optimization in our real-time studies. Okay, and finally, in the second half of this lecture, I will be showing or demonstrating you the software that is Design Expert, and I can solve any of your research problem in regard to optimization. If you have any inputs regarding that, I would be happy to, work in conjunction with you. Okay. So let's not keep it as a one-sided conversation. Rather, it should be an interactive one where we both will talk and discuss like how to propel things and all. So basically, I think to start with, I would first like to hear something from the audience. Like, what do you think? Like, in your after hearing the topic, how it can help you in your research? Like, have anyone adopted RSM based optimization in their studies previously? So, an open question to the forum, because I know a few of you must have done that. So, anyone?
Yeah, I'm Prajit Nambiar from
Okay,
University of Mumbai. I have
okay,
used RSM and Placket Bowman for media optimization studies,
that's great.
but
Okay,
but
so
I
what
have
area?
used
Yeah,
Minitab.
pardon, sir. Could you please repeat once again?
Yeah, I have used Minitab, not Design Expert.
Okay, Omnitab. Oh, it's at the end of the day, it's the same, similar thing, I should say. So that's great. That's great to hear from you, sir. So, anyone else, or any blunt idea like what it actually does? I would rather start with a very small example. I hope we, all of us who are present over here, are using smartphones, Android smartphones, or iOS based phones, whatever. There you must have encountered, a an app which is very well known, Clean Master or something like that. So what does this app? What is the function of this app? This app is actually it whenever we launch the app, whenever we run that app in our mobile phones, it starts with like cleaning up of your junk files, removing of the duplicate images, okay, blurry images. So it will initially do some cache file clearing and all these things. It will free up some of your unused RAMs, close few of the unused apps, okay, few of the unused tabs. So it does a lot of things in order to bring your mobile phone under the best working condition. But remember, here's a glitch. The thing is that it cannot increase uh, the the system boundaries. Like, what do you mean the system boundaries? Like, suppose your mobile phone have, one, yeah, 128 GB of space. So that optimization, that Clean Master or something, any app similar of that sort, cannot increase your bandwidth. It cannot increase your phone memory from 128 GB to 256 GB. Rather, what it will do, it cannot increase your RAM from 8 GB to 16 GB. It cannot do that. But whatever utilization, whatever cleaning up it can do within that particular boundary, that it does. So that is the beauty of optimization. It cannot increase or decrease your system boundaries. Rather, it fine tunes all those system boundaries so that we have a good approach. We have a best outcome under that specific circumstances. So this is the first, I mean, uh, objective or hypothesis of optimization. Like whatever system boundaries we do have, those things cannot be changed, cannot be manipulated, cannot be tampered, cannot be replaced. Within that frame only, we can mm, actually fine tune and get the best optimized result. Now, there are many approaches of optimization. Initially, when we were, before I get into the presentation, I just like to speak a bit. So, before we start the thing, like uh, what sort of programs we are doing in optimization, there are a number of approaches. Initially, in our when these approaches were not valid, not favorable, not, I mean, discovered, we used to go for OFAT, or one factor at a time. Where what we used to do, we used to initially screen some parameters for our experiments, which we call them factors, and we determine the levels of the factors. Like this is the higher level, this is the lower level, and uh, with all these permutation combinations, we try to find out that which is the best optimized output. So where we were playing with only one factor at a particular point of time. But in this case, in optimization, but when later on it was found out that when such interactive terms were there, like the factor, suppose an experiment have 5 6 factors or a number of factors, there could be some outputs or outcomes which were derived from their individual interactions. Like factor A, how individually we are saying that a factor A is good, factor B is good, factor C is good. But when we are coming to a real-time experimental scenario, we can find out that they are also having synergies among them. They can propagate the experiment, they can I mean, downgrade the experiments. So individual interactions were very important in a real-time system. So this was the first thing that instigated that how we can we can create an optimization platform. So thereafter, nowadays we have so many approaches for optimization. We have, so anybody would love to say any other any optimization tools or techniques that you have already heard or worked with that, like sir told us that he has used Minitab. So apart from sir, anyone else? No. Okay. So there could be machine learning approach. There could be ANN approach, artificial neural network approach. There in RSM also there could be so many approaches. Like we have CCD, central composite designing. We have BBD or box Behncke designing. So today I will be focusing only on BBD because look, these are, you must be knowing, these are very hefty things, and completing covering all these things within one session, that is 3 hours or 4 hours, whatever, even a week, it's next to impossible. So I will talk about the very technical know-hows of box Behncke designing, and I will also talk why did I choose box Behncke designing um, as the statistical optimization tool. So before that, I would like to ask a question to the forum. Like, suppose you must have done factor reduction and all in experimental studies, because sometimes we have so many factors in our, you know, so many factors in our experimental system that we have to shortlist or choose the factors. So in such facets, what you all used to do? Because it's a learning for me as well from you guys, because all of you are so much established in your particular field. So I think it should be an interactive session rather than a boring lecture. So anyone else, like how do you reduce factors or choose the particular factors which are important for your experimental analysis? Anyone? Anyone? I have you used this? I mean, have you ever tried of reducing the factors? Because most of the times, literature review, yeah, we definitely deal these things with literature review, but sometimes this literature review, whatever we are getting or whatever we are adopting from the open literature sources, are not sufficient enough. So in that case, principal component, I think you must have heard about that. Principal component analysis is a very specialized technique for this. One of the very important software through which we can do this is SPSS, which has been developed by IBM. So that SPSS is a very important software. It's very similar to that of Excel and Microsoft Excel, where we can get uh, uh, you know importance of the different factors. Say, for example, in an experiment, we have identified around 20 to 30 experimental factors, which are directly or indirectly, I mean, directly or indirectly working with the, you know, affecting the experimental results. So, but in if we try to adopt 20 factors in an experiment, it will become so hefty. Like the design of experimental design will be so much lengthy. It will be really problematic for us to solve that. So, in order to bypass that solution, we can adopt for LCA. I sorry, PCA. So I'll just present my screen. I hope my screen is visible to all. Is it?
Yes,
Yes,
sir. It is visible.
yes, sir.
Thank you. Thank you. Thank you.
Yes, sir.
Okay. So just let's suppose you have 25 factors or whatever. A, B. So now when we need to understand that when we should, like, how these factors are playing a role. So for that we can after you do a principal component analysis. So that's another different thing to talk about, which we can talk sometime later. I mean, so sometime later when if we get another chance. So over there, what we do, if we compute all these things for each factors, we can get an eigenvalue. Okay, EIGEN eigenvalue. So we heard about eigenvector, so that is eigenvalue. So and we found, and at the end of the day, when this analysis is over, the system will provide you with a scree plot. So the spelling is SCRW, scree plot. So it's somewhere like that. Okay, this is how we get a scree plot. So where over there they will indicate factor A, B, C, D, E. Now, in order of preference, they will give this value. So we have eigenvalue, and based on that eigenvalue or eigenvector value, we can get such type of scree plot. And now, if you suppose you require three experimental factors, so you can select from the top three. You require four, so you can select from the top four. So it totally depends on your experimental modules. Okay. So this is a very important parameter. SPSS is not a free software, but there are other PCA computing tools as well, which are available for free. But most often, when you are applying for some high-end research journals, you are submitting your manuscripts over there. You are going for factor reduction. So they generally ask for PCA results from SPSS, which is globally accepted. SPSS also gives a free 10-day duration for practice session, but you cannot export the results from SPSS directly. That's one of the negative part of using SPSS. But anyway, so this is how you can get your parameters screened. Now, just for your information, whenever we are going for a a factor, when we are selecting a factor for a statistical designing, there should be at least three factors that we should select. We should not select less than two factors. Now, what is the purpose of selecting two, three factors? What is the theory behind that? So we all know the concept of degrees of freedom, right? Anyone? What do you mean by degrees of freedom? With a proper example, like how we can evaluate degrees of freedom. Well, could anyone tell me the formula of degrees of freedom? Well, generally, degrees of freedom, the formula is n minus one. So, so if we have seven or x number, let's suppose seven. Yeah, number of independent values of variables. Absolutely, not saying, sir. So I would just give a very short, small example. Suppose the example, the mathematical formula is n minus 1. So if we have five factors, our degrees of freedom will be up to 4. Now, why this concept? How this concept crept in? So just assume you are sitting in a room where you have four walls, right? In front of your wall, in back side, at the right hand side, and then the left hand side. Now I gave you four colors. Okay, so red, green, blue, yellow. Say for example. Yeah, yeah, Dr. Datta, whatever you said, it's absolutely correct. We keeping one factor constant with any others. That is basically the concept of OFAT, or one factor at a time, where we can keep one factor constant to actually. No. Sorry, I think I got it wrong. Keeping one factor constant, we can change the other. Anyway, so degrees of freedom is something. So you have four words. I gave you four colors: red, yellow, blue, green. Now the hypothesis is like you can only use one color for a single wall. This is the term and condition. So first, I asked you to choose the wall which is in front of you. So out of four color, red, yellow, blue, green, you can choose any random color for creating for coloring that front wall. So let's assume you have chosen green. So that green color is gone. Okay, you painted the front wall with the green, and the green color is exhausted. Likewise, you go for the back wall. There also you have three choices: blue, yellow, and red. So I chose yellow over there. So I colored yellow in the back side wall. So now I have two more walls left, and with two more colors, the left and the right. In the left hand wall, we have the red and blue option. So you can select any one. So let's assume I selected blue. So I colored that left hand side wall with blue. And now we have only one wall left with one color only. That is the right hand one with red color. So now just look, you don't have any option over here. You don't have any choice over here. So you're bound to color it red. But for the remaining other three walls, you had your liberty of choosing the color as per your choice. So that's the beauty. That's the beauty of degrees of freedom. So whenever you are, so for any number, your freedom will be restricted to the second last variable. Whenever you are going to the last variable, there will be no such coloring options. Okay. So that's the concept of degrees of freedom. Now coming back to my question, why do we need to have at least three independent variables in an experiment? So the first thing, the first factor, I mean, the first and foremost important is that if we are selecting two factors, okay, then there will be no degrees of freedom, because if, look, whenever we are doing modeling, when we are doing statistics, it's totally a probabilistic model where the system will, consider every possible interactions between the factors at different levels. Now, I will come to these technical terminologies like what are factors, what are levels in the due course of my presentation. I'm just giving a back end story of the things. So that is indeed very important, because if we don't provide the system with the degrees of freedom, then the system won't be able to optimize the results for you. So there lies the major component, like why we should choose at least three factors. Because in whenever we are selecting three factors, we know that it's the degrees of freedom will be two. Two means we still have freedom to choose our boundaries, to choose our interactions. But if the factors we reduce it by two to the number two, then n minus one equals to one. So here you don't have any degrees of freedom. So degrees of freedom is a very important concept, and likewise, it is very important to develop why we need to have at least three factors for your experiments. So whenever you are doing an experiment, suppose you are considering the formation of nanoparticles, or rather the antimicrobial efficacy of nanoparticles. So there could be n number of factors. So from there you can choose three, four, five, n number of factors you can choose from the literature, from your own research, and thereafter you can shortlist those parameters based on the eigenvalue or the scree plot that can be done by PCA, and thereafter from those ranked parameters, ranked factor list, you can select any three or more than three for your optimization purpose, right? So now this is the very basic fundamentals which are required for statistical optimization of a system. So I would love to hear any questions from you before I move to the presentation. So do you have anyone who would love to add up, would love to ask any questions that we have done so? Anything?
Hello, sir. This is Dr. Namrata Ray.
Hi.
Sir, hi. I don't really have a question, but what I wanted to say here is like what Arunima Datta madam has said. Like, I'm a chemist, and when we set up a reaction in a lab, suppose there are 3 or 4 variable parameters. We study the temperature or pressure or the catalyst, varying the catalyst and all that. But the thing is that there we have to have just one variable parameter, keeping the rest constant. Like if I keep the temperature and the pressure fixed, and then study say with 5 solvents and see which is giving the best result, and then once I have identified the best solvent for the system, then I fix the solvent and then maybe vary the temperature of the catalyst. So in a real life chemistry experiment that we would do in a lab, we actually get to vary only one uh, parameter. I just wanted to add that, not a question really.
Yeah, absolutely. This is the conventional thing that we do in our most of our basic research. If we talk about the scientific or the pilot scale research, this is the most widely adopted tool. Whatever Namrata ma'am said, it's absolutely perfect, absolutely correct. But again, that question pops up that what about the interaction between the factors? Because the factors also have their own interactions when they are working actually in a system. So that's the probabilistic model, that's the permutation and combination things that we have to consider, and that fetches better result. So I will also share one case study in the course of my lecture, in the course of my presentation, where it showed that initially there was a study where the enzyme cellulase, we all know what cellulase enzyme is. We were harvesting, we were segregating and isolating cellulase enzyme from one of the microbes, right? So initially, when scientists did a conventional study with one factor at a time, or FAT, what we call, they obtained an efficiency of around 8 point something. But when they adopted optimization, the result almost doubled. I will show that work. Okay, I'm not getting into more details inside that, but just imagine that has been doubled up. So that's very important. That's how the industries are really cracking the things that we are unable to crack at our lab scales, because they are adopting these high-end, precise, and accurate methodologies, techniques. Now, you must be wondering, as I told you, why do we choose this optimization, BBT-based optimization? There are n number, like there could be machine learning, there could be artificial neural network, okay? But the most, I mean, nowadays ChatGPT has made our life really easier. I don't know, it's a positive in a positive or negative sense. That's a debatable issue. I'm not getting into that. But previously, before that, knowledge was really, we need to really pull up our socks and push our paddles to get a week, sir, asked some question while selecting PCA companies for April. We are the values of equipment variance by each component, only one criteria. No, sir, Avik sir, there could be so many criteria, but PCA altogether have a different matrix. So once you input all these parameters, suppose you have 10 parameters, suppose, example. So whenever you will be putting those 10 parameters, they will be giving you a template of experiments. The software itself will give you a template of experiment. Like, do the experiment in this format and give me the output. So based on the number of variables, they will give you an experimental chart, experimental template. You have to fill out those templates by doing those experiments inside your lab. Or you can also simulate the data. You can also use literature reported data if you have that quantum of literature data. But generally, such gigantic volume of literature data are not reported because these data are very particular. They will tell you do this experiment at 35.7 degrees centigrade, at 1.5 atmospheric pressure, okay, 3.18 pH. So I'm just giving a hypothetical example. They will give you such critical measurements. So finding those accurate data in literature is really tough. So once you have done that, then only they will automatically generate the scree plot. And as I showed the scree plot, so from the scree plot, you can actually, based on eigenvalue, you can select the parameter. So it's the graphical representation is a final version. Now there are a lot of back end processes that keeps happening in PCA. But yes, we can also compute PCA by using eigenvalue. We all know the vector scalar things that we have learned in physics. So with those mathematical applications, we can also compute also. But that computations become very much critical when we are using a real-time experimental scenario. Okay. Now coming back to thank you for pointing out, Avik sir. It was a nice question. Now coming back to the thing that why BBD based or RSM based optimization is very important. Now, if we consider ANN or ML, artificial neural network or machine learning, but literature reports that they have better prediction accuracy as compared to BBD. Okay, but you have to understand that there are a few glitches. The first glitch is that if we are considering ANN based model, okay, there you need to have a basic coding knowledge, maybe in the form of MATLAB or Python or R, whatever. There you need to have some basic, coding knowledge, without which it will be really tough for you to actuate those things. Same goes with ANN and ML, both of them. But if we consider RSM based approach, so that does not actually require any background coding knowledges, and I assume that with the faculties or the scientists of these basic sciences or life sciences, we generally don't have that much foundations on computer languages and all. Although we learned all these things, but those were just for the namesake. Most of us, I'm talking about the majority. Please, if somebody knows that, it's absolutely a very good thing. But I'm talking about the majority, statistically significant population I'm talking about. So it's really hard for them to gather all those knowledges and pick up the optimization process, particularly person from the scientific fraternity, not from the engineering fraternity. Because in engineering, we know it's all about quantification, it's all about numericals, it's all about numbers. But in science, it's everything. Our research is more qualitative. So, but nowadays, in whatever research we are doing in our lab, in order to get them transferred, whenever we are talking about technology transfer or whatever, there need to be some particular quantification, or else getting funds nowadays, research grants nowadays is really tough. And trust me, if you adopt this scheme of optimization in your study, it will really help you to manage time, manage your resources, manage, and all these things will definitely have an impact on your overall economy. So it will make sustainable, as we know that sustainability has three pillars: the societal benefits, the economical benefits, and the environmental benefits. So here, in order to make a process sustainable, we need to ensure that these things are being taken care of. Now, and one another important drawback of RSM versus other things is that in RSM we get a particular equation, a model equation. Suppose I'm just giving you an example. I have three different parameters. Okay, I have chosen three different factors: time, temperature, and concentration. Okay, so let's assume the time is from zero to 1 hour, 60 minutes. So this is the range, we call it range of time factor. If we talk about pH, so pH, let's assume from 2 to 6. And uh, concentration is up to 10%. Okay, so 0% to 10%, we are checking like what is the optimized results for all these things if we are producing I mean going for a product. Okay, so this is a very critical thing that when we will do some experiments, when we will put this informations in the software that I will show you in the due course of time, the experimental design will be given by the software, where there will be around 15 experiments if we have selected three factors. Now these factors will have particular values, suppose pH this much, temperature this much, time, whatever factor we have chosen, they have particular values. Now, and you are computing the outcomes against those particular 15 experiments. Now, what if I asked you a parameter or a series of parameters which are not indicated within these 15 experiments? So for that, you have to redo the experiment in your lab as per the conventional studies. But in RSM-based optimization or RSM-based approach, you will get an understanding, like you will get an equation where it will be comprising of all the statistical significant terms, and considering that particular range, whatever inputs you will provide within that equation, it will give you the result with a plus minus of 5% deviation, below 5% deviation, which is considered to be statistically insignificant. Because if the percentage p-value is more than 0.05, then only it's statistically significant, as we all know. So it is giving you a statistically significant result without doing any experimentation. But remember, the boundaries should be the same. We cannot compute. Suppose the pH was 2 to 6, and we need to understand what will be the value of this experiment at pH 9. We cannot do that because that's beyond the boundary. So whatever is there within the boundary, that can be solved and mitigated by this equation. So once you have developed the equation within that particular system boundary, you can compute any random data points without doing any experimentation, and you can predict. So that is the beauty of statistical designing, right? That is the uniqueness of box-Behenken designing, BBD modeling. Now, so that makes RSM stands apart from the other things. Now, what about the in under RSM category also? There are so many things that we can take care of. Like, but sir, but that will be theoretical, right? How to verify the result without experimentation? Yeah, because that is not theoretical at all, madam. Namrata ma'am, because you have developed a model, a statistically significant model, that I will show you how to develop that model within that stipulated boundaries of all the factors. If you go beyond those factors, then the model is not valid. But within that factors, the model is valid. It's like an equation you have developed. Okay, so it's absolutely statistically significant. I will show you. Now, considering the RSM, inside RSM, there are so many things like, as I told you, BBD or box Behenken designing. One way, but without experiments, how can we predict results? Okay, Dr. Datta, I will come back to your answer while I am giving you the demo, because if we have defined an equation like Pythagoras theorem, you have defined a Pythagoras theorem equation, right? I mean, not you, definitely Pythagoras. So, but within that Pythagoras theorem or equation, whatever, you can put any values and get the results. For that, every time you don't have to actually mark whether it is correct or not, because that is the beauty of optimization. You are, at the end of the day, you are coming up with a unique solution, unique deliverable output in the form of an equation, where you just put those things in that equation. Suppose x into pH minus y into temperature minus. Now, this is not a linear system. First, try to understand this is a quadratic equation, which is actually a 3D in, that is what response surface methodology. So we are not we are considering the entire surface, entire sphere. Okay, so that's how things work. It's you are statistically validating the model within that particular time frame, within that particular not time frame, my mistake, within the particular system boundaries, so that you don't need to focus on any other aspects. You just put whatever equations you have and you can get the results. I will show one of my research paper. I think my screen is already shared. Just bear a moment with me. I have to find that paper, just a moment. Okay, no, although this is not a very good paper, let me show you something good. So this paper, I think this is the one. Just a break, just a moment. Yeah. So this is one of the research that we published during my PhD. It was in the year 2021 in one of the Springer publication of the Springer Publication House. Dr. Srimantri was my thesis supervisor. So what we did in this study, we did not adopted PCA in this study because there were only 5 parameters. Okay, generally PCA is considered when you have more than 7 to 8 parameters. What we were doing, I'll just give you a brief of the study that will definitely help you to understand the context of what I am speaking about. We took rice straw, okay, which is a waste biomass. We treated that rice straw. We know that rice straw in countries, in places like UP, NCR, Noida, where not Noida, I think UP and all, where agriculture is the major occupation. So at the end of the harvesting, this rice straw faces serious issues related to the storage, transport, and management. So at the end of the day, what they does, they just burn it in the open air, and which in turn create a gamut of environmental concern. Right? They help in the smog formation, and we know all these things. I'm not getting into all these details. So what we try to do, but just imagine even if we burn those things for generating energy, this is not sufficient enough, because we know that these biomasses have a good content of moisture. So that in turn reduces the calorific value of the biomass and make it unfit to be used as a fuel. So what we proposed through this study, that if we preheat the temperature, the rice straw at different time, acid concentration, temperature, particle size, and solid liquid ratio, we can see good changes. Like, we know acid treatment dehydrates the biomass. That is very well known. So when it is dehydrating the biomass, so that's the agenda. It is reducing the ash content. And another important parameter of this biomass-based energy is ash content, because when we burn these biomasses, they have so much ash, residual ash, which might result in the clogging of the broiler or whatever energy systems we are using, energy generation system we are using. So we took the rice straw, we treated them under different conditions, okay, at different factors. And just imagine these levels, like time 1 to 5 hours. How did we define that? We used this experimental in one OFAT initial experiment and saw that up to 3 hours it is going up. Thereafter it is becoming almost stagnant. Same for acid concentration, same for temperature. But look for the solid liquid ratio and the particle size. They have improved, but thereafter it has remained more or less constant. Okay. So from there we selected that time, acid concentration, and temperature are very good factors in our experiments. So what we did that with this. So this is the standard experimental format of PVD matrix that I will show you in my presentation. So we did all these things and we got some results. So the as I told you, there will be 15 sets of experiments. So you can see there are 15 experiments over here. And when those 15 experiments we carried out in our lab in triplicates, we provided the results. So after that, now you see over here, time you can see only 1 or 3 or 2. 1, 2, 3. Only 3 intervals are there. Temperature 80, 100, 120. Only 3 intervals are there. Temperature 10, 20, and 30. Only 3 intervals are there. And within the 3 intervals only, the permutation and combination matrix has been provided to you. And after solving all these things, we had found out a equation. Where is that equation? Yeah. So this is the template equation, and this is the actual equation that we found out. So let me zoom it. So HHV, or the calorific value, because the performance of a fuel is measured by their calorific value. So under there, you can see HHV equals to 9.3 plus this into time plus this into temperature plus acid concentration time square acid concentration. So this is the equation that has been developed. Now just think. So as I was telling you over here, temperature are defined in 1, 3, and 2. Time, sorry. So now if somebody wish to know that what will be the response when the time is, say for example, 2.2 hour 30 minutes. The temperature is 90 degrees centigrade, which is not indicated over here. The acid concentration is 12%, which is not presented over here. How we will find out? Now, just assume that, just think that all these factors or levels I'm talking are within the boundary. Time 2.5 hours is within the boundary of 1 to 3 hours. Temperature I asked 110 degrees centigrade. That is within the range of 80 to 120. Acid concentration I say for example 25%. That is within 10 to 20%. So all these variables should be within the system boundary. And whenever you will put all those things into this equation, it will give you a statistically significant result at 95% confidence level. Because in equation 1, if you look into this equation, the standardized equation, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 components. But if you look into this equation, 1, 2, 3, 4, 5, 6, 7, 8, only 8 components are there. Why are the other 3 components? They have been removed because they were not statistically significant. You could see that the p-values were higher. So the statistically insignificant terms we have removed. And thereafter we obtain this equation. Now this equation is valid under that system boundaries. And likewise, we will also get some model equations model graphs like this thing. These are interaction plots where HHV will be there in one axis. So over here we have chosen. Now it is impossible to look for 3 parameters at a time because we cannot go beyond 3 dimension, right? So over here, response we have to keep in 1 dimension, that is fixed. So factor AB, BC, and CA. So we have checked how these are actually impacting our study. So this is the fundamental that how we look. And moreover, I will show you another result, the model predicted response curve. Yeah. So here you can see this is the model predicted HAG value and the experimental HAG values. So this is the best fit curve. So you can see all the model predicted and experimental values are more or less within 5% confidence interval. So you can just look into the accuracy of these results. Like whatever the model is predicting, the experimental value is almost very same to that. Even if there is a bit of fluctuation, that is less than 5%, which is statistically acceptable. So this is what our agenda of optimization is all about. So now, if we consider the if we look into that, how within RSM also there are so many techniques. As I said, there is one of the prominent technique is Taguchi method. One of them is central composite designing. One is BBD, box membrane designing. I've learned PBRSM completely by a lot of trial, so still answer this lecture one for. I will definitely, sir. I will answer all your queries. I will definitely come back to your queries when I will be showing you the results. I mean demonstration of the software. I think self-learning is the best learning. Even I also learned, although my supervisor, my seniors helped me out with these things, but still at the end of the day, you have to learn it by yourself because they will give you only overview. You have to get used to the software and all. So it's a very good thing that you have learned it by yourself, and I hope you will propel it further. Now coming back to my answer, we are trying to produce ethanol by using certain. We are using cellulose and beta galactoside. However, we are getting less yield. Exactly is this sort of thing, Dr. Ajay Kumar Das, sir. I will show you one example.
Yes, sir. Yes.
I will show you one example like how adopting optimization have significantly doubled the yield. It's a literature reported study. Okay, I will show you that. Now, in RSM, in CCD is mostly important when we are not sure about the terminals of our factors. Suppose we have a factor of time. Okay, now we don't know at what should we take it at a second level. Should we take it at a minute level? Should we take it in an hour level, days level, years level, months level? We are not sure of that. There, in such scenarios where the terminals of the system of the factor is not very much prominent, not distinct, we need to adopt central composite designing. If we are talking about Taguchi, so that's the drawback of CCD because it's very enormous, very gigantic. You have to put a lot of effort in order to obtain a good CCD result. But it's good when you don't know the terminals of the factors. But in BBD, this is okay. Whether you know terminal, okay, whether you do not know it, it's not a problem. You can. So basically, the optimized setup through experimental data is set boundary. How to know how many such data will lead to formulation of correct equation? Yeah, that is a system-defined phenomena, madam. Dr. Ray, I will show you the real-time system operation, tool operation in the due course of time. Over there, you will get to know that how these things are generated. It's very easy. It would hardly take. I mean, look, the optimization software. It will take hardly 1 hour to. Like I showed 15 data set that will be generated by the system. Okay, it's not something that I have developed. It's the system will develop. Okay. So, in case of Taguchi is a very efficient tool, and one of the most important aspect of Taguchi is that whatever in BBD we need to have at least 15 experimental runs. But in case of Taguchi, the runs are very less. It is around 9 experiments for adopting the entire model. So when we should adopt Taguchi? Taguchi's optimization tool we can adopt. Suppose you are using few of you are doing an experiment where few of the factors are very costly. Suppose you are working on a gold nanoparticle or platinum nanoparticle activity efficacy on a particular mechanism. So gold nanoparticle, platinum, these are very expensive, right? Or we can also think in such a manner that you are doing an experiment where you really have a limited resource. You have so much, I mean, so less resource, and that is you cannot collect it further. The time is gone. You have left that place. Anything could be there under the sun. In those cases, we can adopt Taguchi, where because we need lesser resources. For 15 experiments, you will be at least requiring 15 days. But for 9 experiments, you can do it in 9. So you are saving around 40% of your time. Okay, mathematically speaking. But one of the important drawback of Taguchi is that for every parameter, it will give you a results like this. But this is the signal and this is the noise. We call it S is to N ratio. Signal is to noise ratio. Now, signal is your actual response, and noise is the unwanted response that has, I mean, crept in with the signal. Now, sometimes whenever we are look, Matt, sir, or madam, whoever you are doing, I mean, whenever we are doing these experiments, optimization is like a whenever I think you all have used ChatGPT, Claude, whatever. Beside there is a just below that there is a disclaimer that ChatGPT can make mistake, Claude can make mistake, Gemini can make mistake. So double check your facts. This is a disclaimer that every response will give you. So likewise, every optimization tool will also give you. We need to understand that these are not foolproof. Foolproof in the sense, although they are statistically significant, but even sometimes even 1% deviations can also give you poles apart results. So in such cases, not only BBT can suffice you, you have to initially go for RSM. Thereafter, you have to go for AIML. I mean, ANN modeling or ML modeling. They have better accuracy. If I talk about the modeling accuracy of ML, it's always less than 1% if you do it properly. For ANN also, it's around 1.5 to 2%. So ML, as of now, ML is the best tool as of my opinion, because people kept on arguing that ANN is better. Some says ML is better. But whatever I have learned in the due course of time, ML gives much better response as compared to ANN. But there, as I already told you, you need to have a prior knowledge on computer coding or a brief of these programming languages. But in case of Taguchi, you are getting this signal is to N ratio. So you have to observe whether this, whatever noise it is showing, whether it is correct or it is a part of the signal, and vice versa. Whatever signal it is showing, is it a part of the noise or it is actually a signal? So that confusion is this is a very prominent thing. And this actually can turmoil the entire experimental stuff if you are not confident enough with your factors. So that is one of the major drawback of Taguchi method. So if you are not confident, I think we should not go with Taguchi. We should go with RSM based method. So considering all these facets, every angles, I found RSM based BBT modeling is one of the most safest option for experimental designing. This is again my version of my opinion. Now opinions might vary from people to people, but my opinion, I have worked around 3 to 4 years in my PhD with these tools. So, and my supervisor, he's also a stalwart in this field. So he has been working in this field since last couple of decades. So he also conveyed the same thing. We come to a mutual point that yes, for laymen like us, who are not doing research at an industrial scale. We are doing at a pilot scale. For us, this BBD based modeling is an absolutely best thing. And thereafter, for validation, you can go for ANN based modeling and ML based modeling, like whether your model that you have developed through BBD is good, fair enough to go for that. Mostly in case of industrial aspects, the further validations are being carried out. Not only one or two responses are recorded. Okay. So, any questions as of now? It's almost 1 hour. We have been, time is flying, like anything. So, do you have any queries, any informations? Am I making it boring or anything? Suggestions is well accepted. I will move to the next stage thereafter. Anything would you wish to recap, repeat, or you have not somehow understood, or rather, I have failed to make you understand anything such? Well, in that case, the chat box is always open. You can always post your queries over there. Now I will go to my presentation, and I think, ma'am, up till when do we have this first session?
12 noon.
12 noon. Okay. So fine. So I don't think within that half an hour we can actually, and the next session will start immediately, ma'am, after 12 noon, or there will be some gap.
Yes, yes, sir.
Oh, it's a continuous thing. Okay.
Mm.
So there are, right after that we will go to the software section. I mean, I will go to the presentation section. I will demonstrate my presentation. I will take a short break thereafter for 5 minutes, and then we can go for the actual hands-on. This Design Expert, it's a paid software. It's you cannot get it for free. But yes, there are crack versions available in the market. But what happens with the crack version is that they are backdated, they are not updated properly, which is why they are unable to give you or generate proper responses. And most importantly, mm, whenever you are submitting some research into some good journals and you have optimized your data, they might ask for the validity of your license, like whether your software is still workable, still there, I mean, in the working condition or not. That they need to understand. Then they might ask for, because all this data, whatever we are doing, it's stored in the cloud at the end of the day. So it can be validated if they have your license, the license key, so they can validate the results from any part of the world. Okay. Now I will go to the presentation. So I hope my screen is visible to all.
Yes, sir.
It is visible.
Okay, thank you. I am not able to see the chat box right now because I have put it in the full screen mode. If anyone have any questions, you can just stop me and I can just talk about it. So now first we should talk about the motivation of today's session. Although it's very late to talk about motivation, but still, what make us to shift to make this paradigm shift from conventional experimentation to modeling based experimentation? So these are the four things that I have summarized. First of is biological complexity. Since our just one thing, this optimization is not only limited to biological science. It can be adopted in any field. Okay, technically in any field. But since it is we all are biological sciences researcher over here, so I am focusing under the purview of biological sciences and allied sciences. So we know that biological systems are very complex. Although we most of the time we go for linear relationships, but non-linear relationships and multivariable systems are always there inside a biological system, which makes the biological system as one of the most complicated and complex. We all know these things, so I don't need to go further in this direction. If I talk about the second factor, The traditional OFAT, or one factor at a time experiment, often fail to capture interactions that may have lead to suboptimal or non-reproducible results. Now, this is a very important term, non-reproducible results. Most of the time, what happens, you are doing an experiment in Jammu Kashmir, the same, and you have optimized it over there by doing one factor interaction. You have not you have not considered the interaction terminologies. So that is something very problematic. That experiment cannot be replicated, or even it is not. If even it is replicated, you are not getting that particular results when you are doing it in the southern part of the country, where the temperature is around 35-40 degrees centigrade, and you have done it previously at Jammu and Kashmir, where it was around 10 to 10 degrees centigrade. So there will be here and heaven. I mean, statistically significant difference between the obtained result. Okay? If you're doing it in the open system, not in a closed and controlled system. So that non-reproducibility is one of the major threat for our biological science experimentations. So that could be solved by using optimization, because we are not considering OFAC, we are considering these multivariate systems and non-linear relationships. Okay, so these two things have been taken care of. Now, if we talk about the third thing, it's about limited resource. Now, as I always talked about, optimization, be it Taguchi, be it RSM, BBD based modeling, we only have to do a very small segment of experimentation. But remember, if we have done that by using OFAT, we have to do so many experimentations, and that too not getting a proper reproducible result. So, limited resource. So, resource constraint is a very important matter that could be addressed by this BBT-based modeling. And finally, statistical designing. Once we are doing it, statistical designing plus modeling, so it works on the RRO cycle. So what is RRO cycle? The reproducibility, the robustness, and the optimized. Okay, so these are the three things that a optimized result convey. Okay. In the meanwhile, since we will go for a mock optimization, I would ask the audience who are there, they could put any we can go for 3 to 4 experimental designings, because we will be having around 1 hour for that, for the software demo. You can select your, if you have any prior experiment where you wish to obtain the experimental design, you can frame it, you can write it as per your convenience, and when we will be doing that, the actual hands-on demo of the software, we can use your data, or else I have to put some random data which might not get good result. So if you have anything, you can share it with us so that we can simulate the results with those data. So limited resource and statistical. So these are the 4 pillars that why you should adopt optimization rather than one factor at a time. Okay, yeah, but the thing is that if we talk about optimization, there are 2 major drawbacks. First of all, having these costly softwares are really sometimes problematic for colleges and universities to procure, because our education system is not very much oriented towards engineering aspects. The big shot engineering institutes have all these softwares ready, but if we talk about our science based basic science based organizations, they lack in this software. So for that, what you can do, you can collaborate, you can get your data. There are so many firms, so many companies which help you to optimize your data. I think I got a message. Is there a message I got? Minitab has said, what if I optimize it in this way? Yeah, you could do that within that period, but again, that will be a problematic, because if a reviewer asks for your license key, then you will be unable to share that. So that's a glitch. So most of the journals don't ask for it, but yeah, if you, I mean, I publish around 13 to 14 papers in optimization field till date, and only twice I got this comment, "Ki, please share your license key with us." So I had to share, because or else the paper would have gone into the toss. So that's a problem. But for the free version, it's a problem. So it's better if you can get this work outsourced or collaborate with someone who have this access to the software. Because see, at the end of the day, these are very basic softwares in engineering institutes. Okay, in institutes like NITs, IITs, they almost every lab have these simulation softwares. Can BBD give same different prediction for? Yeah, it can. It can, Dr. Chakrabarti. It can give different results, because I should not say different. I should say more precise. Suppose a BBD based optimization is showing that your system have 3% error. Now, if you just, I would like to show you something. If you look into the result part of the equation, there is a term, this E. What is this E? This is error. So if the error is more than 5%, then only it will be there in your equation. But see over here in the actual equation, there is no E component. That means the error is below 5%, which is why the model is valid, and we have not included that in our experimental research in this data, in this model. But to answer the question, like, can BBD and different have same experimental design? Obviously, it can have. Suppose BBD, as I told you, CCD is a bit advanced as compared to BBD. Okay, so not we can sorry we cannot compare between BBD and CCD. These are all under RSM. Mostly they do not give different result. But if we compare it with Taguchi, or Taguchi with ANN, Taguchi with ML, they could have different results, because ANN is a much upgraded version as compared to RSM. ML is a much better version as compared to ANN. So if the error percentage is suppose 4% in RSM, it could be around 2% in ANN and 1% in ML. So definitely the results are different, but it is getting more precise, more accurate. So it's not a better, it's not a different result, but a better result. Okay. I hope Dr. Chakravarti, I have addressed your queries.
Yes, sir. Thank you. Thank you so much.
Thank you. This is a software. Okay. So, any questions as of now? Anything would you love to ask? Okay. So we would love to move to the next section. Traditional versus modern method approach. So this is a very important. I have tried to, and thanks to AI for all these transformations, I have tried to transform all the text into images. So I really believe that images have a better resident time in our system as compared to theory. So if you wish, I can share this PPT with the convener ma'am, and she can share that in your group. I will definitely do that. And as I was talking about in the previous slide, so if you don't have the access to that software, you can you can collaborate with some research community who are doing this work, because at the end of the day, nowadays, we are facing multiple rejections. But just think, if engineers who are from engineering institutes, they are publishing so many papers. How they are doing that? We are facing so many problems to publish a single paper, and they are publishing so many papers within that single time frame. All thanks to these optimization techniques, because they are so vibrant, so so precise, so robust, so reproducible. They can give you excellent outcome with a very limited resource. So you can there are so many companies, industries, so many organizations who can help you with your optimization part. So you just talk about your problems, about your experimental problems, and they will efficiently sort that. And they will adopt, not only they will consider BBD for that, they will get you the best result for best approach which you should adopt for your research. So if we consider traditional approach and modern approach, like what are the main differences? So definitely in traditional approaches, we initially go for one factor at a time, and I already talked about. We do trial and error. Like, is it happening? Is it happening under this scale? If not, then what scale? So all these trial and error methods are not there in, not pertaining in this modern statistical designing. And finally, whatever results we are getting, they are suboptimal and non-reproducible. But just think, if we move to the next segment, that is the modern statistical designing and modeling segment. Now this could contain BBD, okay, this could contain ANN. So it's not about like the only I'm talking about BBD. It's true for all the optimization approaches. Okay. So they talk about non-linear relationships. So first it was only y equals to mx plus c. We were considering a linear scale equation. But in a quadratic equation, things is not like that. It is, so linear means it is only 2D. But whenever we are going for quadratic, it is in the 3D mode. So you could always compare that. If you're viewing a big photo of the globe in a paper, and we are actually seeing the earth in the form of a globe, I think the second one is better in 3D orientation. The same goes for this modeling approach as well. So it is reproducible, it is robust, and it could be optimized. So these are the key differences which actually makes these approaches poles apart from our traditional methodologies. So anything to ask as of now? Am I able to, you know, express myself? So any questions, I would love to hear from you if you have, or else I would move to the next slide. Okay, fine. So moving on to the next slide. Now, what are the limitations of these conventional OFAT experimental schemes? So the problem is that we don't consider the interactions. So technically, what we do, we in traditional approach, we change one, we keep the other variable constant. We play with variable 1 and measure. Thereafter we change the variable 2 and keep other thing constant, likewise 3, and we keep on measuring. So the problems are that we do not know how in the real-time system 1 will interact with 2, or 1 will interact with 3, or 2 will interact with 3. We don't have any idea regarding this thing. But in RSM or BBD based responses, that is a surface methodology, it's actually like a box, black box, okay, where what's happening we don't know, but we are playing together with all the parameters. Okay, so they focus on modeling of interaction. They are efficient in multi-factor exploration. So if we are just imagine, if I gave you an experiment with 12 factors, it will require at least 2 to 3 months to complete all the experimentations, if we are doing in a conventional one factor at a time approach. But if you are adopting this RSM based approach, even if you have hundreds and thousands of variable parameters, you can easily get it done within a couple of days. Now, if the experimental duration is higher, we cannot ignore them. Suppose we have to do an experimentation which incubation period is 2 months, suppose. So we cannot bypass that thing. We have to wait for that. But the other time parameters could be reduced. Okay. Definitely there we have fewer experimentation, which is a very important facet. As compared to the traditional approaches, we have very fewer experimentations in modern approach. And over here, what is the other important is that there is a predetermined matrix. You don't have to determine like what is the uh, like whether we should take this data point or not. Some might say ki, we need to keep these data points. Suppose you have a pH from, not pH, you have a time period of 1 to 30 days. Now I might ask you to keep the I mean, the particular 1 to 30 day time frame, you divide it in 30 intervals. Someone can came up and say, you please divide it within 5 fragments of 6 unit each. Some can come and say, you just take 0.5 interval and keep it at 60 intervals. So there is, I cannot say you are wrong, I am wrong, or he is wrong. Everyone is correct in their own perspective. So there is no standardization like which one to adopt. But in this particular modern approach, in this particular field, you don't have to define all these things. All these things will be preset and predefined by the software, by the tool that you will be using. So if I now coming to the response surface methodology, what is response surface methodology? Now it's like there are three components of a RSM based method. The first is modeling, second one is optimization, and third one is prediction. As I told you, modeling is like you are modeling the thing, like what are the factors, what are the levels, which factor to choose, which one we should not choose, and how we can get a optimized result. Optimized result is in the form of the equation that I showed you. So this is the, and that can be also used for prediction also. As I told you, if there is any data point which has not been considered within that 15 experimental data set, we can predict those data points by using that equation. So that's a very important parameter of response surface methodology. Okay. You can see in a real, so actually the surfaces are like that. So there could be n number of peaks. This is a typical response surface plot. Okay. And this is a standardized plot. Like out of all those data, they have just done this normalization. So this is what it has been shown over here. So now if we move to the exploration, so this junction where you are getting the best result. One more thing that I forgot to mention earlier, that whenever you are putting all these method factors and levels, after optimization, the system will give you so many outcomes. Like this could be the results. I would show you one example. In the previous paper that I was showing you, in this work, the optimized condition was like, so the system will give you so many optimum conditions. Okay, so these are the optimum conditions, and where the highest. So our intention was to improve the energy content, right? Because we were using that rice straw, which was not fit for fuel as a fuel. So we are putting that in the software matrix and getting an optimized result, right? So now you could see the system have shown you so many permutations. Like if you keep the temperature at one time at 1.9 hours, temperature at 120 degree, and acid concentration at 20.6, you will get this much of HHV or calorific value. But our aim is to find out that which one is the highest. So this 5.22, 16.522, this was the highest response recorded with the increment of around 22% of the value. So initially, if the value of calorific was around 100, so now it was around 122.64. So this is the optimized result we finally concluded with. So the system will give you so many outcomes. And now there could be some outcomes which are not good. How to determine whether the outcome is good or not? Those are determined by this D optimality index or D index. Okay, what is D index? D index is just like R square value, which varies from 0 to 1. So the more it is close to 1, the more accurate is the result. So over there, all these values are less than 1. So we have not considered these values. Now among these four values, all are good with good D index. But you can see it's only 16.504, 511, 522, 504. So this is the best result we could evaluate. So this is the optimized outcome. So that is what being defined in the PPT. So we could go for optimized and best result prediction. So I optimize, and now prediction is like, as I told you, once you have the response ready with you, the response, I mean, you can check any of the response, but within that factor space. That is very important. So any questions as of now? Now I will come to the most critical part of today's session, that are different terminologies which are being used. Okay, so these things you need to understand at a very minute level, because every time people will ask you what is a R square, tell me that address is R square. This, once you know this terminology, it will become much easier for you to understand the real-time experimentation. So factors. So the factors are what are things we can change or control in an experiment. And I have also put some examples from our real life so that we can actually correlate like how we can play with that. So if it is like factors, as I always kept on telling that you need to have minimum 3 factors and all. So if it is a factor, then it's something that we can change or control in an experiment. Suppose you are doing a as someone said previously, they are doing some chemical synthesis. So chemical synthesis requires a lot of factors. It could be temperature, it could be pH, it could be the reagents, okay, it could be the catalyst, whatsoever. So when baking a cake, so what is the example? When baking a cake, factors can be like temperature, time, amount of sugar. So all these things are factors. Now you can raise the temperature as well. You can I mean, you can raise the time, you can manage the time, you can adjust the amount of sugar to be added. So all those things can actually differ, and like optimizing all those things will only give you a good cake to bake. Okay. Thereafter, the levels. So now, as I said, there could be n number of factors. For every factor, there will be some level. So the level is, suppose temperature. Suppose I'm considering temperature over here. So temperature might be 150 to 210 degrees centigrade, as per you. So this is what level is all about. And there is also another important term, that is range. So range is always the higher limit minus lower limit. Okay. So it's, if I consider these are the to be these three to be the levels, then 100, 210 minus 150. So 60 is the range of the data set. Then we go for the output or response. So output is the outcome. As I said, in my experiment, the outcome was the increment of calorific value. So in this experiment where we are baking a cake, we know Christmas is coming. So more or less we all will be either baking a cake at our home or we'll get it from the market. Anyway, so how do we evaluate it's a good cake or it's a bad cake? Definitely the freshness, the taste, the aroma, the texture, all these things describes that how good the taste, how good the cake is, and accordingly the price also varies. So over here we can evaluate the softness, the taste score as the outcome or response of the factors of the experimental designing. Now the immediate next thing is that fit summary. What is fit summary? So fit summary is a report that shows how well the chosen model explained the result. So it's not only necessary that whatever experimental factors we have chosen, either by doing OFAT or by doing PCA or by doing literature survey, whatever fit summary we have got, we have obtained, whatever uh, whatever results we have obtained by using those uh, factors, whether those factors were well chosen, whether those factors are fitting exactly to give you the best outcome. So these are all falling under the domain of fit summary. Okay. Thereafter, we have p value and f value. So if I come to the fit summary of example of a fit summary, so it will tell us whether our cake baking experimental model makes sense or not. So whether apart from time, temperature, and amount of sugar, so is amount of sugar is a good choice for baking a cake? Is time a good choice? Is temperature a good choice? Or rather, we should eliminate one or two of them and introduce some new factors, or we should keep them and introduce some other factors, because we cannot go down below three factors. So these are all coming under field summary. That explains how whether we have chosen this good factors or not. Now, all these things, although these are sounding too much technical, I know for the maybe many of you are here listening to this for the first time, but trust me, all these things the software will do for yourself. You just have to obey the software. You have to just follow the orders that the software will be giving you from time to time. Nothing else. So now the p value and the f value. So p value, it shows if a factor is important or not. As I told you, initially there were 11 factors in an experiment in the model, but when we finally developed the model in my paper, if you remember, there were only 8. There were only about 8 factors. So what about the other 3 factors? So their p-value was greater than 0.05. That is the threshold. So if it is greater than 0.05, then it is not considered. If it is below than 0.05, we can consider it. Okay. And f value, it shows the strength of the effect of the factor. So if the f value is high, so it is showing that it has a good impact on the outcome of the experiment. Okay. Thereafter, we will go to the predicted and the adjusted R-square. So these are very technical terminologies. Predicted R-square and adjusted R-square. So predicted R-square, it will indicate that how well the model predicts your new results. So we know that R-square is a value from 0 to 1, right? It varies from 0. Sorry. So it varies from 0 to, it might vary from 0 to 1, R-square value. So the more it is closer to 1, the better is the result. Just like the d-optimality index. The more it is closer to 1, the better is the result. So now, that is a predicted R-square initially. Now, what is adjusted R-square? The adjusted R-square is like, as I told you in the last example, there were 11 factors initially. In 11 not factors, 11 parameters in the equation. But when we put those things in the real time, we do the statistical analysis, we found that out of 11, only 8 are good to go with. So when we removed all those parameters, all those 3 which are not statistically significant, then we get a better R-square value. That is called the predicted R-square. Because why we are getting a better R-square value? Because we are removing the other things, the predicted, the statistically insignificant terminologies. Okay. Now we are moving to the next one, that is lack of fit. What is lack of fit? It shows whether the model matches with real experimental data. As I was telling you, okay, this is a very important parameter, whether it is good or not. Like it is, look, whatever we have done, the final thing is outcome. So whether whatever your model is predicting, is it close or near or accurate to that of the experimental result? That is determined by lack of fit. So it shows whether model matches with real experiment. So if a lack of fit p-value is high, then the model is good fit. So if the lack of fit p-value is low, then the model is not a good fit. Okay, so these are the basic terminologies. We have some other terminologies as well. So I have jotted down 14 such for terminologies which you need to understand before you are moving to the actual uh, simulation modeling. So degrees of freedom I have already explained. I am not getting into that. The number of independent pieces of information available for analysis. So you have 5 data points. The degrees of freedom will be 4, which is equal to n minus 1. 5 minus 1 equals to 4. So I think you are clear with that. So what is sequential model sum of square? So we have, I think, another 1.5 hours, I guess. Ma'am, could you please confirm the ending time of the session? Is it 1:30 p.m.?
Yes, sir. 1:30 p.m.
Okay, so we have good quantum of time. Okay, so that's sequential sum of square means it will check with the model whether it's a linear model, it's a quadratic model, or a cubic model, and explain the best results step by step. Okay, so like it's just like you first check the small cakes, then the medium size cake, then the big size cake, and you are experiencing that how with the change of shape and the change of size, the taste and the quality of the cake is changing. Okay, so that's what the sequential sum of squares indicates. So under which is the best model fitting for that? That will be the sequential sum of squares. Moving on to the next definition, mean square. So mean square is the average variation based on the sum of square divided by the degrees of freedom. So it's a mathematical experiment. So it's the average variation based on the sum of square, okay, and with divided by the degrees of freedom. So basically 8 divided by 9 is this divided by this, we will get the mean square. Okay. So if we talk about the example, then how much cake softness changes between different batches on average? So you are doing a batch size of, say, for example, 10 per batch. So in the first batch you took out 10 medium size cake. In the second batch you produced 10 small size cakes. So now what are the variations in batches? This indicates the mean square. Moving to the ANOVA, I think this is the most important terminology in RSM. So ANOVA, we all know it's the analysis of variance. So it's a table that helps to decide which are the factors statistically significant and affecting the outcome. Okay, so only by using ANOVA only you can come to the conclusion that we need to select these parameters and not these parameters. So it's a table like ANOVA could tell you like whether time or temperature has more impact on the softness of the cake. Whether time is playing more role or the temperature, which has the more efficacy towards producing a better cake, better quality cake. So this is ANOVA. So ANOVA will help you to eliminate the statistically insignificant terms and thereby refining your model, fine-tuning your model, and give you better result for the model. Talking about fit statistics. So fit statistics is a number that shows how well model performs. Okay. So it's a consortia of everything. Like when the example can include, like when we are driving a car, in the dashboard there are so many indicators. The fuel, like how much fuel remaining in your tank, what is the speed in which we are driving, what is the average mileage right now. So considering all those facets, we can predict that in how much time we can reach to our destination. So all these facets, all the different, so field statistics is not a singular term, it's a consortium of different things that requires R square, predicted R square, and standard deviation. Most importantly, apart from that also it considers a lot of physics. Next, normality plot. It's a graph used to check if experimental score errors are normally distributed. So if the distribution is normal, then it's good to go. If it follows an abnormal pattern, then there is some problem with your model. And finally, the d-optimality, as I told you, it's a value that might range from 0 to 1, and the more it close towards 1. Look, in real time experiments, we do not get a exact value of 1. That is impossible to achieve. But yeah, a value of around more than 0.85 is good to go with. But in real system, even you can get a value of 0.4 also. Okay, so there, if you are getting a very low d-optimality index, that will in turn indicate that your choice of factors are not good, or you have not considered their interaction too much. Okay, so there could be, so in short, the fit statistics was not good. So this is, so if the fit statistics is very low, automatically the d-optimality index will go a bit low. So I am just putting these slides for 2 minutes over the screen. Please go through these things, and if you have any query in any terminologies, I can re-explain these things. Else, we will go to the next slide. Although these are very minor statistical things, I hope you all might be new, but still. Okay, so should I proceed with the next course of action? If anyone have any problem, you can still ping me in the chat box. Now, there must be a question like, why RSM works better than OFAT? So it's a pretty, it's a question that we should actually indulge into. So first and foremost, it captures interactions and not linear effects. So generally, you can see in case of this RSM, so it is considering under the domain, it is considering all the data points, all the possible data points it is covering. But here in OFAT, there is some discrete. So if between these data point 1 and data point 2, there is a huge gap that has not been addressed. Similarly, for every data point, you can see there is a gap which has not been addressed. So if I mean to say, we have not considered those data points, the effect of those things, those points, and this in turn makes our prediction, hampers our outcome. In case of time management, efficiency and all, so this is an OFAT, which is an exhaustive thing. So you can just consider, so if it is a time frame, So there are so many dots we have to consider if we wish to cover the entire segment. But here, if we wish to cover this entire segment, there are relatively lesser number of data points. But look, it has a very good pattern and it is covering almost all the areas. So it has covered almost all the area. But over here, the it has covered that much area only, but with so many data points. It's almost 5-6 times, I guess, if I compute this thing. Okay, so this is one of the advantage of RSN. Third one advantage is prediction capacity. So if there is any untested condition, but again, remember within that domain, within that frame, within that range, then this could be addressed. This could not be addressed by OFAC, but this could be addressed by using the RSM approach. And finally, optimization. So with this thing, you can easily find out the apical value where we are getting the best results, or we need to reduce it. So where the response is almost low. So here in these areas, the responses are very low. Okay, the outcome would be very low, and here the outcome would be very high. So if you wish to improve something, go for these points. If you want to reduce something, go for these points. So accordingly, you can find out the optimum and the optimum result with statistical confidence, and definitely with forecast predictability. So you can forecast that if something is there within that time, within that years, what will be the result within that factors and levels, what will be the result. So this is how RSM is a better choice as compared to OFAC. So anything you wish to? Anything you would wish to ask me? Okay. So now overview of experimental designs under. So as I was talking about, so there are some other things also apart from RSM, there are other optimization tools also. So like if you are using a full factorial design, so these are full factorial is usually for preliminary screening. It's like a full range scan that we do in case of a UV visible spectrophotometer. If we don't know the component, we don't know their best peak where we will get, so we can do a full scanning. So that is actually a full factorial about preliminary screening. It is typically used to identify significant factors when many variables exist. Okay, so in this entire scan, we can find out that where are the peaks we are getting and what is the best thing. So when we are using, so that's a full factorial experiment. That's basically an OFA. Then we go for the CCD, or the central. We are go for the CCD modeling, or central composite designing. It widely explores the star points and good when the extremes are safe. So we during the extremities, during the terminals, CCD is a very good thing, as I told you. Box Benkin designing, it's like something where we don't have much knowledge on coding, we don't have much knowledge on signal to noise ratio. All these things could be taken care by this BBD designing. And there could be other designings also. They have different special approaches as per their events. Okay. So so considering all these factors, I consider BBT as the safe zone because I don't need to have any prior computer coding knowledge. I don't need to evaluate whether whatever the outcomes is given by the system are correct or not. That I don't have to evaluate. It is already auto-corrected and within the statistical definitions. So if we move to the deep, if we give a deep dive into the BBD structure, so complex, I mean, if we wish to look into the concept and structures. So the first thing is that the very first thing, as I already told you, there should be at least 3 factors. This is true for any optimization. Okay, there should be at least 3 factors, and for all the factors, there should be at least 3 levels: the higher level, the lower level, and the mid level. So technically, we should have 2 levels. The mid level can be computed by using the higher and the lower level, taking the average. So you need to have the highest and the lowest level in order to get the significance of the factor. Secondly, you need to understand that box Behn designing or BBD designing it avoid extreme corners. So for that, I would like to show you something. So let's assume this is a black box. Okay, first of all, can anybody tell me the steps of a process? Like if I'm considering a process, what are the steps of a process? Generally, a process runs on the three things, right? Input, processing, and output. So it runs on the IPO cycle: input, process, and output. So input, we can have at least, as I told you, we need to have at least 3 parameters. In process, it's like a black box. Or what's happening, we don't know. And output, we can have one or more output. Okay. So let's assume for keeping it simple. So this is the simplest IPO cycle, where there should be at least 3 input parameters, 1 processing unit, and 1 output. Okay. So now, if we consider the box Behn model, so it's like a box. Okay. Just consider you are sitting within a cubicle room, and you are exactly trying to fit a ball within that room. So the ball is exactly fitting the walls, but I mean it will touch the midpoint. If it is an ideal condition, the ball will touch the midpoint of all the 6 walls: 1, 2, 3, 4, upper level and lower level, 6 walls. But it will never get the readings of the corners. That is very important. It will not consider what are there in the corners. So in order to get the best fit, the ball will be like this. Now, if we wish to get these extreme corner values, we have to pull the ball at this. The shape of the ball will be distorted, and likewise, the ball will not retain its original shape. So the model will be hampered. So that's one of the fundamental, what should I say, thing that we should consider while doing a PBD. We cannot get the extreme values, but it does not consider the extreme values in order to put in a balanced state. Okay. So that is what it has been shown over here. So there should be at least 3 factors per level. Now for every factors, there should be 3 levels. It avoids extreme corners for safe designing, because if we wish to go to the extreme corners, the model can be distorted. Okay. So this is ideal for biological and pharmaceutical contexts. Okay. Finally, there are fewer runs. So in case of a full factorial, if we are doing a 3-factor study and we consider a full factorial experiment, there will be at least 27 runs. But if we adopt BBD over there, the run will reduce to 15 to 17. So it's around a 40 to 50% reduction, around 40% reduction. So you can see it's a good decrease. And finally, it is rotatable. Rotatable means it depends on the distance from the center, not in the direction. So so as I was telling you, if it is a ball fitted within that, so from the midpoint, every corner is equivalent. But if we have considered these extremities also, then these extreme points will be higher, longer as compared to these points. So it is rotatable and uniform. So these are the 4 considerations we need to keep in our mind when we are doing the box Behn designing or the conceptual designing. So these are internal things These have nothing to do with our experimentations, but we need to understand these things. Now, please remember this extremities point. I will further extreme corner this. Please remember this point when I will be telling about the experimental design. You will be more able to correlate with this time with this thing. Okay, I will come back to the in the next course of my slide. Now, the workflow, like what we should, how, from where we should start and how we should end. So first, we have to get the preliminary screening. So narrow down to the few influential factors. Now, first you have to understand the factors. Like these are the factors used in my study. So you can use literature reports. You can use PCA. Okay, you can use OFAT, whatever. And finally, get to the conclusion that these are the factors which are influential in my studies. But remember, it should be at least 3. Then, once the factors are determined, you have to go for the levels, determine the levels of the factors. So what is the highest point, what is the lowest point, and what is the midpoint? So that will give you the range. So now your factors and your levels are determined. Okay. Now going to the third one. So in the third one, what will happen? You have to generate the you have to, once you have the factors and their levels, and you put all these things into the mini tab or design expert whatsoever, it will generate an experimental matrix for you. This matrix is same irrespective of whatever you are using. If you are using mini tab, it will be giving you the same matrix. Even if you are giving design expert, it will be the same matrix. Okay. So now it will give you at least 15 experiments. Now remember these 15 experiments, there are only 13 experiments, and I mean it's always 12 plus 3. So that last 3 experiments are for errors. So these 3 are basically same. So for the first 12 experiments will be different. 13, 14, and 15 are same. So technically you have to do 13 experiments, not also 15. Because if you are confident about your factor selection of the factors, you might not, you can well assume that there will be less error. Okay. So generating all these things, you will get a matrix. Now, those matrix, you have to perform the experiments in particular matrix. Whatever 15 or 13 matrix the system will provide you, you have to do those experiments in lab and record those data. After recording, you have to put all these things in the software, and now all these things from 5 to 10, the software will do. So these are the portions, this 1, 2, 3, 4, this you have to do, and the remaining 6 things, the software will be doing it for you. Okay. So what they will do, first they will find a fit summary, like in which model the system is best fitted, in linear, in quadratic, in cubic. Okay, that need to be defined. Next, immediately they will go for statistical analysis. Like as I told you, it will look for the p-value, lack of fit. It will do all those things, whether it is your system is in the good sync or not, good synchronization or not. Okay, whether your model is good enough, it is statistically significant. It will first compute the R-square. Thereafter, it will compute the adjusted R-square. It will remove the statistically insignificant terms. It will include the statistically significant terms. It will see the lack of fit, goodness of fit. Actually, lack of fit could be also termed as goodness of fit. Okay. Thereafter, so once the statistical model is validated, it will go for the RSM and the contour plots. So the RSM and the contour plots are nothing, but these will show you hotspots. Like these are the areas where you are getting the maximum applicable response. This is the area where you are not getting good response. So all these things will be provided by RSM. I mean, provided by the response service methodology, response service curves, and the contour plots. Both have similar function but different representation. Some says it is easier for us to understand through contour plot. Some says it's easier for us to understand through response service plots. But eventually, they both denotes the give you the same understanding. Okay. Okay. So right after that, once this interaction plot have been established, you understand that how you can work with the the system, how you can work with the parameter, how you can work with the output. All this has been fixed. Now it will give you a target value. I mean, optimized figure. Now this optimized figures is like, as I told you, there was around 22% increase in the calorific value in my study. Okay, so all these things it will be shown through this optimization, like this is the best. Now sometimes we don't need to find the apical response, we need to find the minimized response, like where we are getting the most lowest outcome. That could be also one of our studies. So say for example, we are trying to eliminate some infection of a microbial population. We want to reduce them because they are infecting us. So we are putting some other external agents and determining under what condition we are having the minimum infection. So for this we call it negative optimization. Okay, generally optimization is for positive maximizing, but for minimizing also we can use optimization. That is also a very important parameter. And finally, validation experiment. So this is a very important part. This also you have to do it, although the system will give you some inputs. Like apart from all these 15 sets that initially the grid will generate, apart from that 15 sets also, the system will tell you some other list of experiments. We call it testing data. Okay. So initially this is known as training and this is known as testing. So this testing or validation experiment, they will tell you, chalo, do these experiments in this is standards and show me the result. So once, actually what it will do, it will compute that results by using the equation that you have developed, and also you are giving the experimental output also by doing at your laboratory or whatever. Okay, so you are giving that data also. So now a system, the software will match how close the values are. So if it is very close, it's a good fit. If it is not very close or more than 5%, then our model is not correct, we have to redo it again. And finally, we have to document everything properly so that we get the full optimized results or assay. So this is the workflow of BBD is optimized. So it's a very important slide, and thereafter we will go to the software. So could you please let me know, like, anybody have any problem in understanding up till here? Because we are almost at the end of the demo, I mean presentation, and thereafter we will go to the software demo, because I think we have around exactly 1 hour left with us. If you have any anything else, factor A, factor B, factor C for your experiment. Okay, I think I have a question. Uh, Video paused. Okay. Is my video visible now?
Yes, sir, you are visible.
Can you see the template slide, like BBD template slide?
Yes, sir. Yes, sir.
Okay, okay, fine. Cool. So these are the runs. So as I told you, there are 15 runs. Okay, 1, 2, 3. So likewise, look, these 12 runs are different, but in the last 3 runs, these are all same 0, 0, 0, 0, 0, 0, 0, 0. But these 12 runs all are different. -1, -1, 0, -1, +1, 0. You cannot find any repetitions, but only these 3 things are repeated. So if you wish to save your resource, you can omit these things and these 2 experiments. So you do this once in a triplicate and put this data, so that you can do. it's if your resources are limited, but it's better to do 3 times to actually get the error component. Okay, so these are the factors: factor A, factor B, and factor C. These are the 3 factors I talked about. So now, what are the meaning of this coding? So -1 is the lower limit, 0 is the middle limit, and +1 is the highest limit. Okay, so now compare this. So this is the generalized matrix. So whatever factor, suppose you can name any factor. You have, suppose, just let me put it side by side. Suppose you have time, temperature, and pH. These are the 3 factors of your experiments. So time, let's assume it's within the range of 3 to 6 hours. Temperature is in the range of 50 to 100 degrees centigrade, and pH is around 2 to 8. Okay, so over here, so this is A, this is B, this is C. Now this for this factor A over here. Okay, this factor A, I mean, I'm considering this column. Okay? So if we consider this column, it will be like -1 will be 3, 0 equals to 3 plus 6, 9, 4.5, and +1 equals to 6. Likewise, for factor B also you have to compute, factor C also you have to compute, and you have to run these operations. So in the first run, A is -1. So A is -1 means time will be -1 means 3 hours. B is -1. That is, temperature will be -1 means 50 degrees centigrade, and pH is 0. 0 means 2 plus 8, 5, 10 divided by 2, 5. So the middle value is 5. So you have to run the experiment in 3-hour time, 50 degrees centigrade, and 5 pH, and get the result. Likewise, you have to do this 12 set of experimentations, or rather 15 experimentations. Is it understood? It's a this is the only thing you need to understood, and the remaining things will be eventually taken care by the software. Is it clear? Like how to code the factors and the levels?
Excuse me, sir.
Yes, ma'am.
Is Arunima Datta. I have put 2 questions in the chat box. Would you please?
I'll do that. I'll definitely consider. Is it compulsory to run pilot experiments before applying BPD? I didn't get your question. Pilot experiments in what sense?
So pilot experiments in sense that we can have an idea of what are the parameters and what can be the expected outcome, then run it in wet lab, and then we go for BBD to set up finally.
Yes, that will have to do eventually. That will have to do eventually, because you need to justify your parameters. Like as I told you, you can see that we have chosen the time to be 3 hours to 6 hours. How could you conclude that it's between 3 hours to 6 hours? For that, likewise, you can adopt like the scheme we have adopted over here. This is even if we are increasing our time from 4 hours up to 5 hours, you can see the response is almost linear. So these are the preliminary experiments we have done before entering into the BBD. So
Actually, sir, sorry to interrupt. Sir, I am from zoological background. So in my research, we had used mice as a model, and we incorporated gender-based, gender-biased, as well as time and dose-dependent actions we have predicted. So in this case, if we try to design the experiment based on BBD, we can go for a varied kind of varied dosage and varied components also, as well as time and gender biased experimentations. And then we can get an idea how to plan the experiment and then run it over BVD.
Indeed, Dr. Datta. This is exactly
Sir, I'm working in a very remote place in Chhattisgarh, so we don't have direct access for animals or that kind of a best laboratory facility that I used to had in BHU. So for this, I wanted to know that can these data or these experimentations, the outcome of these experimentations, they are well accepted for proposing projects or writing review
grants.
articles, right? We can.
It's a very important for grants, madam. I should emphasize, if any of the grants, if you are putting these approaches, that makes your project more industrially, more tangible. The
Right.
product is more tangible, right? So that will definitely help you to I mean, that will give you a benefit. I'm not telling you that it will definitely secure the brand, but the probability will definitely be higher. That's for sure.
Because earlier in these funding agencies, they used to put much effort in what are the practicality of the
Yeah.
experimentations. Have you done it in your wet lab, or you are predicting the results? So by using this BBD method, we can justify that yes, these are the predictive outcomes, and now we can go on for the wet lab experiments
You
to
are getting
justify.
the predictive outcomes, and you are also validating that in the experiment. I mean, in the lab. So you are getting close value. That suppose you are doing 5 data tests. You took any 5 random data series definitely within your system boundary, and you run the experiment.
Right.
You will be getting some results. Say, for example, 1, 2, 3, 4, 5. You are getting 5 values. Now, whenever you are checking that with the model that you have developed within that same boundary, this is very important. Within that same boundary, then you can, and you are getting 0.9 in place of 1. Although the result is close, but that is statistically insignificant because the difference is 0.1, which is 10%. But in the second case, you get 1.98. So that is very close. That is okay. So suppose out of 5 experiments, 3 results are statistically significant. So majority wins, and that's the basic fundamental of statistics. Majority wins.
Right.
So okay. So these are all supportive things. I am not telling this is exact. This is accurate. Precise. Precise.
And then we can argue that because of this precision or high level of significance, we can go for producing this data and reproducing in other conditions which are at par, or maybe be having certain different parameters, although it will be reproducible, and these are the predictive results, and we can go on with the study. Right?
Absolutely.
Acceptable in the science.
Actually, at least it will help you to find the range. Chalo, my response will be within 14 to 16. Yeah, whatever value. So you got that range. So out of the whole universe, you have defined a very narrow range. So that's your achievement. That's your contribution to the scientific community. That chalo, don't need to work in such a huge environment. So just narrow down these parameters, and you will get 95% accuracy.
Right.
So nothing is better than that, I think. So next question was, or we can input basic data.
This one is being taken care of, sir.
Yeah. Okay. So
thank you, sir.
Most welcome. So this is how you need to code the experiments, okay? Because as I told you, BBD or whatever only understand binary digits. It's always 0 and 1. So once you have developed this matrix, you have got this data. So there will be also another column, output. So for every experiment, you need to put the output X, Y, Z, A, You have to compute the output. And so now look, there will be 2 sets of experiments. So in the first one, you have to put all these things, the factors, the levels, and the system will give you this table. So now you take away this table, go to the lab, perform these experiments, again come back. reopen that program that you have already done. You can save your program, you can save your model, put those datas over there, okay, and now compute. So automatically in the second round you will get the optimization. So whatever you were willing to do maybe in 1 or 2 months can be easily covered within a few weeks, maybe 1 or 2 weeks. So even on an average, BBD will save you around 60 to 70% of your experimental time. This has been globally reported as per various literature. And also, I have also faced, I mean, during, I was about to finish my PhD in 2020, which at that time COVID hit. So it was a very tough time for us to conduct all these experiments because everything was shut down. All have witnessed that. So then, under those constraints, my PhD was at stake. So this really helped me to get rid of this thing because I was working on sustainability. So I used a different software which is known as GABI, which actually go for the LC or the life cycle analysis. So I was more inclined towards that initially at the early stages of my PhD. But thereafter, considering all these facets, I had to make a move towards these optimization tools, and finally, it has given me really good publications and patents. So we also find a patent on that, and that has been published, but not. I mean, that has been granted. So it's there in the technology transfer level in our NIT Agartala from where I have done my PhD. So this is really has been a game changer thing for me, and which is why I keep on promoting this, because being into the scientific research community, I found out that we are not using this in our basic science research. So whenever I get a scope to interact with faculties, esteemed faculties who are the pioneers of educations like you all, so I try to impart this knowledge, transfer this knowledge, so that at least you can adopt this and save your time, which is, I think, very valuable. So I was talking about the case study. I did not got the exact author name and all, so I was just doing in all of the case study I found out where I could only get the information about the journal, so I have not got much details about the study. So the initially what was it was the same experiment, okay, where cellulose yield was measured, okay. So in the first phase where traditional optimization was taken care of, we could see the initial yield was only around 7 to 8 U per ml. But application of BBD study significantly improved because they used box bank designing, the factors were defined, the results were defined, and we showed that, and they showed that the result is around 116.67, which is almost, or it's exactly the double of whatever yield we were getting through OFAC. And interestingly, the model predicted and the experimental results were exactly same. It's both were 16.67 U per ml. So the validation was so accurate. Okay, so this indicates that how initially, I mean, there is a paradigm shift by using this BBD. Now, this is a coincidence where the predicted and actual values are exactly equal. So this is a miracle, I must say. On a general base, 1 to 2% deviations are always there. This you have to take care. I mean, put it in your mind that 1 to 2% deviation is absolutely fine to go with. Okay, so I think I have only 3 to 4 slides remaining. Thereafter, I will just go to the software demo part. So what could be the impact? So I have talked about a lot, like why should we do that? Now, what are the actual outcomes of adopting these RSM or BBD configuration schemes? The first and foremost, that is significant resource saving. If we know that industry, we often it's a joke that we used to crack it during our graduation and undergraduate times, that industry runs on 3 things: money, money, and money, or time, time, and time. Okay, so if that's the thing, then these optimizations can really help you to save time and money both, which are very important parameters. Okay, they require fewer experimentation, less reagents, less materials, So definitely less cost and less timing. So you are saving resources, you are saving taxpayers' resources. Uh, so that's a very important parameter, I think. Secondly, higher yield and better performance. As I showed in the last slide, that initially it was around 7 to 8, but after adopting optimization, it become more accurate and the yield was around almost doubled up. Better reproducibility and predictability. So predictive, I told you, you saw that how good the prediction was. It was 16.67 and the predicted response was also that. So it's very close to the, if you design it properly, trust me, you will get a very close to, and I'd say it's near to the actual results with maximum 1 to 2% deviations. I have found out if you have correctly chosen the factors, correctly chosen the levels. Okay, there now what you just have to take care of two things: the factors and the level. There should be no manipulation in these regards. If you are very much confident with those factors, the remaining things will be automatically taken care of. Okay. Third important, the fourth point is the mechanistic insights and rational designing making. Like it is actually showing you that in which areas you have highest response, in which areas you have lower response. So it's technically taking care of uh, you know all the aspects. It's actually showing you the entire spectrum. From entire spectrum, you can choose any color as per your choice, or it's like a full system UV scan. You can choose any UV peak which you wish to proceed with, and definitely it accelerates your research and development. So whatever things, there were so much hit and trial in slow loops in research, but in optimization it really, it's a very smooth thing. And really I have worked so much with optimization. It's just I try to adopt this thing in every aspects. Although I'm an environmental scientist by specialization, but trust me, I have adopted this in medical biotechnology, in quality control, and it has never failed to amaze me. Every time it has given so brilliant result. So even I'm not an expert of, say for example, I'm medical biotechnology. I have worked with people in medical biotechnology, and this has given me more exposure to different research communities because they have adopted me as a collaborator for their optimization. And since it's a very generic knowledge, it could be adopted in any schemes. So it's really helpful if you can try it out properly. Now, there are some common pitfalls, and we need to understand how to avoid them. First of all, as I told you, improper factor ranges or improper factor selection. Now, sometimes we understand, chalo, if this is the experiment, time and temperature will definitely have a value, have an impact. pH will definitely have an impact, but these considerations are very unsafe, very unfeasible, very unrealistic. So your range should be, and most importantly, once you have chosen the factors, their ranges should be very well, I mean to say, very well defined. Suppose you are choosing in one experiment, you are choosing the range of around 16 units, and in one experiment you have chosen the range of around 200 units. So there definitely will be some unbiased results. So try to keep the range as close as possible. I know it's not possible always, because for pH there is only 15 scales, 0 to 14. But in case of temperature, there is no such limits. Okay, but still, it's very important to bring in a particular close. Okay. Second, ignoring interactions. So how the interactions are playing among within them. If it is not a good fit, we should remove that factor and incorporate new factor. It might take some time, but once the model is stabilized, trust me, the first model that I developed, it faced 17 rejections. In the 18th rejection, the paper got accepted in a Journal of Terror and Francis. And thereafter, that by using that optimized model, I published 2 or more papers immediately within the next 2 years with minimum rejection. Because once the factor is already published, you can always quote to that. Look, that is the published opinion, and from there I am carrying it forward. So that really makes you helpful for the next publication. So the first step will be tough. Thereafter, it will be very easy. Okay. Second, As I told you, validation is very important. You need to validate the model. You need to run validation experiments, not only rely on the model predicted data, but also work on some validation experiments. Okay. Sometimes overfitting. The model is too much overfitted. Okay. Or too many factors you have considered with a very comparatively lesser few runs. So when the number of factors are increasing, the number of runs will also increase. That is very important parameter. And biological variability. So generally, whenever we are, it's also important. Suppose we have developed a optimized model for a gram-positive bacteria. So it's not always, it could not be generalized altogether. Like, chalo, I have optimized it for one bacteria, microbial system. Now it is okay for all the microbial system. No, they have different working patterns. They have different metabolic rates. So these variabilities might be there. So generalization should not be a concept of optimization. It need to be considered from case to case. So practical guidelines start with pilot scaling, okay, or screening phase. When using BPD, there should be at least 3 to 5 variables, not more than that. You should employ standard software, as I said, Design Expert, Minitab, J, R, JNP. So these are all various. Among them, I have used Minitab and Design Expert. Both are very good. Always include center points. Now, do not go for extreme. As I told you, it's a ball that has been fitted within a cube. And finally, after model prediction, always run validation experiments, like whether your model is capable of validating or not within that particular system boundary. That validation experiments are very important. So finally, choosing the right experiment. So BBT, as I said, it's moderate variable should be there. We should not concern about the extremities. Our main goal is to optimize, not explore. If it is exploration, then CCD is a better model. So it's tuning within a known safe operating window, but whereas CCD and other, they are mapping boundaries, identifying non-linearities or complex models. So in short, this is the basic difference between BBD and other optimal designing like CCD and all. So with this, I would like to end up my presentation and go to the software demo. This is my research team, whom we work with. If you wish to connect me through LinkedIn, I have provided the QR code and also my email ID and phone call contact details are there. I would love to hear from you if you have any queries. You can either WhatsApp me or email me. So it's the details are over here. So now I will go to the software demo part. But before that, I would like to ask, do you have any queries? Or should I move to the last segment? Okay. So now, without further delay, I will just go to Design Expert. So this is the interface of the Design Expert. Is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Visible.
Yeah,
Yes,
fine.
sir.
Thank you. So this is a Design Expert. This is 13th version, and it has been made by Statis Corporation. Okay. So over here, you can go for new designing. If you have any designing which you have already stored, so you can open designing. It's like import data. So if you have any, now you know the template, standard template, as I told you. This is the standard template. So if you, without opening also, you can get this template. Okay, BBD template. So for this thing, you don't need to open the software. You have this model and you can just fit in the data over here. So once you have find out that, so you can use through import data. So for us, it's a new design. So let's go to new design. So over here in the left hand corner, you can see the standard design factors. So there are so much. Okay. Under response, since we are doing responsive methodology, we can see central composite designing, DSG or definitive screen designing, optimal. So optimal, you can custom your own design, and box blanket. So we are going for the box blanket. So you select box blanket designing. Now, once you have selected this box blanket designing, now you can see over there. Now, this is a very user-friendly. Why I prefer design expert? Because Minitab, I personally has found it's not that much design-friendly as this design expert software is. Because over here, every operation you are doing, they will be giving you some information about that operation, like what are the key things it should have, what are the factors it should have. Okay, it will tell you. So like each numeric factor is set to 3 levels. So minimum 3 numerical factors should be there. So you can see numerical factor, it could be as low as 3 up to as much high as 21. So if your factor is below 3, then BBD is not the right option. I mean, no optimization tool is the right option. And if it is more than 21, then also BBD is not the right option because you cannot go more than 21. Okay. So let's assume that we let's be minimalistic and let's start with 3. Okay. Now category factors. What are category factors? Now category factors are just assume we are modeling the statistical population of statistically modeling the population of India. We have modeled and we are predicting like in the next 30 years what could be the population of India. So these are progressive modeling, right? So if we are doing in such a fashion, now we need to understand the area, demographic area, the initial population. So these are the range of data is very high, exceptionally high. So today I think the population is around 140 crores, if I'm not wrong, 150 crores, whatever. So from zero, the minimum population could be 0, and the maximum could be 150 crore. Just imagine the difference. So for such huge range data, we use category factors. So for example, if the numeric factor is 3 and we are considering Indian population, so 0 to 150 crore would be the my numeric factor for level for factor 1. Now for category factor, we can split that particular factors into up to 10 fragments. So factor A, it's a very huge range. We have split it down into 10 up to 10 category factors. But remember, whenever we are adopting category factors, it should be equivalent for all the factors. Like for factor 1, we have fragmented them into 5 segments. For factor B also there need to be 5 segments. C also there need to be 5 segments. This is the thumb rule to maintain the equilibrium of the reaction of the modeling. So now, does anybody have any suggestion regarding the experimental factor so I can put and simulate a result for you? Anybody wish to give any response? So let's assume that I am doing my experiment only, whatever I have done in my head. So let's assume that time, temperature, and acid concentration are the 3 factors that I'm playing with. So the first one is time. You can think of, if you have anything in your mind, I can put that as well and simulate that results also. So after that,
Sir, sorry,
yeah.
sir. I didn't. I'm not sure whether this will work, but I did an experiment on designing of antibacterial surfaces. Okay. So we quoted. We calculated charge density on the surface. The variables were time,
Mhm.
temperature, time,
Could
and
you please write it down in the chat box so that I can just
okay. So you need me to write the values or?
yeah, the apical values, the extreme values.
Okay, sir.
Okay, I will just put it. You just tell me. The first factor was temperature.
Yes, temperature.
This is temperature. Okay. What was the second factor?
The second factor was charge density.
Third factor?
And third factor was time. I mean, it was studied for different amounts of time.
Time. Okay. What was the unit of temperature? Celsius, I guess.
Yes.
Charge density?
Just a moment, sir. Yes. I mean, it was ESU per centimeter square.
ESU
Yes.
per centimeter square. Okay. And time? Minutes?
Hours.
Hours. Okay. So what was the highest, lowest value of temperature? I mean, lowest and highest.
Temperature, the lowest one was 37
37, highest
and the highest was 42.
42. Okay. For charge density?
Just a moment, sir. Right. For charge density, the lowest was 1.4 into 10 to the power 15 ESU per centimeter square.
Into 10 to the power 15.
Right.
Uh,
And the highest was
just a moment. 15. The highest. Oh,
the
it must be a
highest.
number. Minimum charge density must be a number. So it should be a whole number. I mean, you have to tell me in decimal.
Okay. I mean, it will have so many zeros.
Yeah, that you have to put because they don't understand that to the power and all. It's you have to put in a linear scale. So in
Okay,
this.
then
So let's suppose
I-
0.05. Let's suppose.
yeah, whatever. Yeah.
Yeah, highest
The
0.2.
highest. Okay, yeah.
Let's suppose, okay? Just suppose.
Yeah.
Yeah. So time?
Time minimum was 4 hours
4 hours.
and maximum was, say, overnight. So we will take like 10 hours.
10 hours. Okay. So now we have put all these informations, okay? These are the initial information we need to have. Now, center points per block. So that is actually the how many times it will be replicating the result. So it's 3. Okay. So if we have 3 is the minimum. I mean the not the minimum, it's the optimum thing. Most of the time we take three runs to get the standard deviation. So
Excuse me, sir.
yeah.
Sir, can we just change the categoric factors to maybe 3 or 4 so that we can understand that there may be various strains of bacteria upon which we are trying to find the charged?
No, the category factors only we can take if the data set is very exceptionally large. Here the range is only 5, 6. If
Okay.
it's in 8 to 10 digits, then only we need to go for category factors because incorporating category factor will make your optimization really, I mean, complicated.
So fixing the numeric factors and categoric factors, we can use the BBD design for I say to check the population density of a particular plant in a forest or something.
Technically speaking, if it is at least 10 lakh, the range is between at least 7 digits, then only we go for category factors. Else, even for lakh also we don't go for category factors. Up to 6 digits also we don't go for category factors. So if it is in the 7 digit, then we should hit category factors, not less than that.
Okay.
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 This is a thumb rule again. You can adopt anything. This is a thumb rule I am talking about. Okay, so once you have done these things, you need to go to the next. Now this is the response. Ma'am, what was your response? Like, what was the outcome of the experiment?
Right, sir. The outcome was optical density measurement. So should I tell you the value then of that?
No, OD, optical
Yeah,
density.
OD. It was OD. Yeah. So the minimum and the maximum value you need?
No. OD, for response, we don't need them all. We need a unit.
Just a moment, sir.
What was the unit for that? No units.
No units, sir. No
No,
units.
so just put no units. Okay. And you click on finish. So once you click, within seconds, it will give you the chart. Okay, so run 1, 2, 3, 4, 15. Okay, and this will follow the same trend as it was indicated in this -1, -1, 0. It may be in a shuffled manner, but all these experiments, all these data points will be there only. Okay,
Okay,
so you
sir.
can tally with that and you will get this thing. So first one, now it is telling you, okay, do the first experiment. Okay, where you need to put, look, this is standard one. Okay, standard one is 37. So 37 was the -1, right? So see, it was,
Yes.
I think it was -1. Look, it was -1, -1, 0. So over here, just let me check. So it was the first one is -1. Then what was the charge density? 0.5 to 2. Look, 0.5. So it is the minus one. I mean the minimum value.
Right.
And hour is 4 to 10. So minimum value, right? 10
Right.
is 7 is
7
the
hours.
minimum.
Yeah.
So 0. So minus 1, 0. That is standard one. And you can go to the PPT. Standard one is minus 1, 0. So this is universal. Okay, no need to play with this thing.
Okay.
This is already there. So it might be shuffled in your interface, but standards will be one, then these two, then these three. Okay. So likewise, it has given the runs. So now you need to do experiments in all these thing, all these parameters. So experiment one, you put these factors and can compute the result. For experiment two, you did these factors and compute the results. Now you have to put all these results over here. Now, ma'am, you just do me a favor. You,
Right.
since you have done the experiment, you might know what could be the possible outcomes. Or within it, you just keep on telling me, and I will just fill it randomly so that I can show you
Okay.
how to get the results.
Okay, sir. What I have with me is
And that will
like
not match with this because that is totally a new experimental set. I don't think these experimental sets you have done in your lab because these are typical BBT template. So you
right.
can just tell me some randomized figure. We just need to check. We don't care about the accuracy. We just need to know the process.
So the thing is that with as with increase in the time, the
Mm-hmm.
optical density say started we started to observe it from a range of value at 0.042, and as time increased with the overnight thing we reached at 0.187. So you can put any values in between for the
Zero
others.
four two two 0.422
Yes, 0.042 to 0.187. Yeah.
0.4 to 1.8. Okay. So let's assume, let's put some random figure. Okay. 0.049. I'm just putting, I'm not,
Yeah,
because
yeah.
now, man, one thing you are talking about only time, but over
Right.
here, you are talking about linear interaction, but it's actually a non-linear interaction. So you don't know in actual system what will be the values because
Right, right.
temperature might be correlated highly with time. Charge cannot maybe highly correlated. So there are so
Yeah.
many technology. I mean, probabilities. So I'm just putting some random figures.
Right, because
Uh,
when the charge density was fixed, it was fixed, and with that we studied how the
Yeah,
OD was varying with time and again at a fixed temperature. So when everything is varying, so it becomes a more complex model. Yes.
yeah,
Excuse me, sir. One
yeah.
thing, before we were setting up the design, there was a command horizontal or vertical. Those
That's
two.
that's not a problem. That's not a problem. That we should ignore. Okay, that's more for complicated designings. Okay,
Okay.
that
We
we
will
should.
always go for vertical.
Yeah, we will always go for
Can't hear.
vertical.
Okay.
Look, there are so many things in the software, so it's practically impossible. Even I also don't know most of the functions because it's like an ocean. You cannot know everything about optimization to be very realistic. Okay, but the thing is that there are at least 10 to 15 parameters that you need to understand, which will actually help you to establish your results. Okay, nothing else. Remaining, there are so many interactions. Even I also don't know. And only talking about BBT. So same thing will be there for CCD. Same thing will be there for Taguchi. You need to at least spend 5 to 6 years of time if you wish to grab a full designing thing. At least 5 to 6 years you have to spend on that. It's impossible to acquire every knowledge beyond that data. I mean, beyond that time. Okay. I'm just give the prelims. I am just giving a flavor that how it can significantly improve your experiments. Okay, I'm just putting random data. I don't know how the data will be coming. So let's assume these are the data we have found. Okay, these are the data we have put. Now we need to go to analysis. This is analysis. Now, as of now, we have not done that, so it is empty. Okay, OD value is empty because we have not set the command. So just click on analysis. Okay. Now thereafter, you have almost now next you have to start some. They will ask for some more comments like the analysis is OD value fine. Now what type of transformation you are looking forward to? Is it a square root? Is it a natural log? It is an inverse square root, inverse power? A lot could be there. So, or even you can put no transformation if if you're unsure like what will be there. So on a technical scale, square root transformations gives a good result. You can use square root, you can use power. Okay, and over here I am just using square root. So if you are unsure of whatever things, I mean whatever transformation you will be taking forward to, you can always use this square root transformation. I mean square root linear regressions into square root model and put start analysis. This is a generic thing. Okay, it might change, the results might change from one category to another. Okay, so if we select natural log, we will get a different result. Okay, so and we can click on start analysis. So once we clicked on start analysis, the entire things is ready. So it's in your fingertips. So first it is telling you the fit summary. Okay, look here it is. Since it's a fabricated data, it has no connection with the real data. So the system is also also very much perplexed like what to show. So initially it is showing that it's somewhere between the linear and quadratic model. It is not into the linear, it is not into the quadratic. So it's actually a 2F1 2FI model, which is somewhere in between the linear and the quadratic mode. Okay, that has been suggested by the system. And if we move on to if we try to fit it in the cubic model, it will be else. Else means the model will be distorted. So that is why it's indicated in red here. Okay, so that is the fit summary. First of all, it is showing that this is your, if that is the value, then it's, sorry sir, it's not a quadratic model, it's not a cubic model, but it's somewhere between a linear and a quadratic model. So you can see the predicted R square is minus. That could not be there, but it's showing minus because we have put random value. If we have put corrected value, its value would come around 0 to 1. Okay, so this data interpretation is very important in this statistical modeling. I think we don't have much time left, but still I will try to cover as much as possible. Then sequential model sum of squares. It is showing the different interaction like mean versus total, linear versus mean, 2F1 versus linear. So it is very close to 2F1 versus linear. As I told you, it is somewhere between. So this is the suggestion it is giving. It is somewhere between 2F1, linear and 2F1. Sorry, linear and quadratic. So that is what the fit summary also indicated. So fit summary and sequential sum of squares are in close synchronization. Okay. Thereafter you go to so once you have done the fit summary, you go to the model. So model terms, it has, so these are the terms that they have indicated, and these are the terms they have not concluded. So many terms they have declined. Okay. So if you go to the model, okay, this is ANOVA. So ANOVA is actually showing what are the factors we should take and what are the factors we should draw. And with this, they are showing you the coded equation. So if we go to the coded or the actual equation, so the actual equation would be square root of OD equals to plus this much minus this constant into temperature minus this into charge density plus this into temperature. So this is the model this is the equation that generated. So this is a coded equation could be also there and actual equation also there. Both are same thing. And this is only the coefficient. So the actual equation could be only found in over here. Okay. You can just, now for getting that data, you just need to open a suppose MS Word or Excel file, whatsoever. So let's assume that I have opened a PowerPoint file. I need to close this one. I just have opened a Okay. So just keep it open and minimize it. Okay. And in the result column, you just click on right click and export table to PowerPoint. So automatically, instantly, it will be exported to the PowerPoint in the last slide. So you don't have to take screenshots and all. You can easily export your data from there. Okay. Likewise, you can export every data. You can export ANOVA table. You can also copy export it to PowerPoint, to Word, whatever. So say for example PowerPoint. So you can see that ANOVA is also there. So this equation ANOVA has been exported. Okay. So this is the equation that you talked about. Now we will be going to the model graphs. So over here, this graphical optimization need to go, go to the graph. Now, since it's a very, we have put very randomized data, so no graph has been generated because it is not correct. Okay, the data are not correct. So I will give you some sample data. So let's suppose we have used this data. So I'm just opening the data for you. So this is the design of experiment. This is the fit summary. Okay. And our fit statistics. So these are the interaction plots. So this is the RSM plot of A versus B. So you can see how the plot is. So it's like you can just go to the software. You can choose A versus B, A versus B. So since the data is very randomized, no interaction has been found. Okay, but if it would have been a real-time data, then you would have get such things. So what is the significance of this thing? That here is the plastic degradation efficiency. Okay, that is the outcome. So pH and temperature were the factors. How these factors are playing role. So this red coding means it is very high. Blue coding means it is very low. So wherever you are getting blue coding, we are getting low data, low outcome. Wherever this red color is there, we are getting highest outcome. So likewise, at this point, so when these two factors are combinedly they are increasing, they are improving the value of the outcome. So this is the interpretation of these results of these response surface curves. So these color coding, these all help you to make exactly, it's a very good representation of your data. So once you have done that, then thereafter you can find so this type of data is there. So this AB, AC, and BC. So 3 interaction plots are provided. These are contour plots, as I was talking about. Both represent the same thing, but in a different categorization. Okay, here also you can see over there also if you remember for factor AB, the lowest was 28.5, the highest was 47.5. So here is also the same data. So we are getting the highest results over here and the lower responses over here. So this is it's more like a heated map. Now, these are the optimized results that the system will give you. Okay? I could not show you in the system because no data has been generated. So no optimization will be there. So what is that? It has given you 100 solutions. You can see the system will give you 100 solutions. Now, all the solutions have since it was a real-time data, look, all their desirability was 1. But the system had selected this one. Now, since all the desirability index of all the values are 1, you can choose any data point from there, and all are the optimized condition. Now, which one is the best optimized condition, that you have to figure it out. Now, suppose what is the utility of that experiment? Now, let's assume in place of pH, it is a gold nanoparticle. So, since the desirability is 1 for all the facets, we will choose this factor with the lowest value, because we know gold nanoparticles are very costly. So in experiments where we are employing, where we are using less costly, less quantity of costly material, that is saving my time. That is saving my resource. money. So we can select this value 6.2, or we can even search which one is the lower. If we can find something in the range of 5, that also we can select. Okay. Likewise, you can use these, play with these parameters to find the exact thing which you will be considering. So I think 6.2 is the minimum. Yeah, 6.2 is the minimum value, not more than that. But the system will give you a balanced one, because system doesn't know whether which one is costly, which one is not costly, until and unless you have defined that. It's up to you how you can select the optimized parameter. So you have select this thing. Now the system have given you so many data sets apart from the of your experimental data that you provided. So you can use any of these data set as a validation set. So what you can do, you can actually take temperature, pH, and this masses to liter ratio. You can choose any one and take the experimental outcome in the lab and correlate them with these results. So if it is close match, it's a very good thing you have done. You have cracked the puzzle. And if it is not, then you have to redo the experiments. There might be some problem with your fit statistics. There might be some problem with your summary. Factor selection, label selection, all these things. So with this, we come to the conclusion of this thing. Now, this is a ramp diagram, where we call it a ramp diagram of the optimized control. So if the temperature is in over here, pH is over here, and cellulose is over here, so you will get the maximum plasticity efficiency, degradation efficiency. So these are the ranges. So it's just nothing, a visual representation of the ramp diagram. Of your experiments, and finally the software building information. So this is the software building information that we have used. So with this, I would like to pause over here. I should say rather stop over here, and this forum is open for questioning if any, or else I am just putting my email ID as well. If you have any further queries, you can write it to me. I think that time is almost over. Okay. So any questions?
Sir, due to shortage of time, we need to wrap up. As
Yeah.
we conclude this enlightening seminar, I would like to express my heartfelt gratitude to our honorable speaker for sharing his immense knowledge and expertise with us by providing an insightful and thought-provoking response surface methodology (RSM), particularly with box Bioengineering design, provides a systemic approach to experiment optimization by identifying optimal condition with statistical rigor. I appreciate all attendees for their active participation and valuable contribution. It's been a pleasure hosting this online literature course, and I hope everyone leaves today with a greater understanding and new perspective on our focus topic. Thank you, sir, and participant for making this seminar a success. Thank you so much.
I would love to hear anything from you. I have already provided my email ID. So
Okay,
once,
sir.
thank you very much for providing me this platform.
Okay, sir. Thank you so much.